In this video, I'm going to go through all of the answers from Midterm 3 in our class this semester. We discussed some of this in class the other day, but this video hopefully will be useful in reviewing as we get to the final exam later on. So the questions here are presented in order that they were on the test, and I will try and put the timestamps for the individual questions in the comments of this YouTube video. So you'll be able to find all the timestamps for where each question started, if there's one of the 5 questions in particular that you are struggling with. So, question 1 was a multiple answer question. So given the tree below, select all of the attributes that are true for the given tree. So the tree has myself and the entire instructional team placed in a random order, which should be a hint towards one of the later answers. So how would you answer this? Well, I would say you should break this down into parts, right? And sort of start analyzing each option, right? Each one of these choose multiple questions is basically a series of true or false questions, right? And that's the way I grade them as well. So this is really 9 true or false questions that just happen to be using the same tree. And the first 3 are related, right? So they all have to do with special types of trees, which this is the relevant section from your Xi book. And the question asks, well, the first question asks, is the tree full? Well, the definition of a full binary tree is if every node contains either 0 or 2 children. And if we look, myself and Ivan have 2 children, and everything else is a leaf, right? It has 0 children. So yeah, it is a full tree, right? The next question asks if it's a complete tree. So a complete binary tree a binary tree is complete if all levels except possibly the last contain all possible nodes. And so the first level contains all possible nodes because it's the root. The second level contains 2 nodes, which is the maximum. And then the last level isn't complete, but everything is to the left, right? Everything is as far left as possible, which is true, right? So that means this tree is also complete. So it's full and complete. And then the definition of perfect, a perfect binary tree is if all internal nodes have exactly 2 children and all leaves are at the same level. And that's not true, right? Because this leaf, right, Seth is a leaf because it doesn't have any children, but it's not at the same level as the other leaves. So this is not a perfect tree. It is full and complete, but it's not a perfect tree. Right? So those 3 are related, and we just got the definitions. But so let's move on to the next question. Right? The next question asks, is it a binary search tree? So binary search trees are defined in that they have this property where all of the nodes in the left subtree are less than the nodes in the right subtree. Well, the root of this tree is Dan, and its left child should be smaller, which Ivan, so D comes before I, which means this isn't a binary search tree, right? This first link violates that property, which means it's not a binary search tree. So then the next 2 questions are about the height of the tree, but let's skip those for a second and go to the depth. So the depth of a node, and again, this is the quote from your Xi book. A node's depth is the number of edges on the path from the root to that particular node. So this question is asking about the node Carlo, which is this guy here. And from there to the root, we have 1 and 2 edges on the path from the node we're examining to the root, which means the depth of that node is 2, which means 8 is correct. And if the depth is 2, it can't be 1 or 3. Right? And then finally, the height is defined as the largest depth of any node in the tree. So Alex and Carlos are the two deepest nodes. Alex and Carlos are the two deepest nodes. And we already know that Carlo has a depth of 2, which means the height of the tree is the depth of the deepest node, which is 2. And if the height is 2, it can't be 3. Right? So this is the correct answer. The ones you should have marked as true were that the tree is full, it's complete, its height is 2, and Carlo is at a depth of 2. Right? Okay, question 2, just like question 1, was basically a set of true or false questions, but now we're dealing with this binary search tree. We're told that the nodes store integers, and one thing that I didn't put in the actual question, but I did mention in the exam channel when somebody asked, in class we didn't allow duplicate entries, right? So this assumes that duplicates will not be inserted into the tree. Right? So again, I would break this down and really deal with it like a bunch of individual true and false questions. Right? So that means we should start at the beginning. And the first one says, true or false, any negative number would be placed at A. Well, we know it's a binary search tree. So we know that from the root, which is 7, any negative number would be smaller, which means we would have to go to the left. And any negative number would be smaller than 4, which means we again would go to the left. And it would be smaller than 2, which means we would again go to the left. So yeah, any negative number would be placed at position A, right? So if we tried to insert any negative number or 0 or even 1, any number less than 1, it would go at position A. So yeah, that's true. The next question asks -3, true or false, -3 would be placed at B. Well, in the previous question, we said that all negative numbers are going to be placed at A. So that can't be true if the other one is true. But then the next one asks about +3. Well, so let's see where we placed, right? So 3 is less than 7. It's less than 4, but it's greater than 2, which means 3 would be placed at B. Yes, that's correct. Yes. And then the next two are related. They're both asking whether 6 would be placed, is it going to be placed at C or is it going to be placed at D? Well, again, let's try and figure that out. So 6 is less than 7. 6 is greater than 4, and it's greater than 5, which means it would be placed at D. So this first one is correct. It's going to be placed at D, which means it can't be placed at C, right? So that one's incorrect. And then the next ones require, again, that duplicates are not entered into the tree. And it asks for a little bit of thinking here, right? So it asks, true or false, there's no number that could be placed at F. So F is here in the tree. And in order for something to be placed there, it has to be, because we're left of 10, it has to be less than 10, less than 11, but greater than 10. Well, is there a number, an integer, that's less than 11, but greater than 10, that's not 10 or 11? There isn't one. So yeah, there is no number that could be placed at F. Right? That's true. Using the same logic, the next question asks, there's only one number that could be placed at C. So again, let's see, we have to be greater than 4, but less than 5. And once again, without repeating a number, nothing is greater than 4 and less than 5. So that's false. There's actually nothing that can be placed at C. The next question asks, there's one number that can be placed at B. So, sorry, at B. Yeah, so at B, we have to be less than 4, but greater than 2. So actually, we already said up here that 3 would be placed at B, but is there a second number that can be placed at B? There's not, right? So only one number can be placed at B, and that number is 3. And then the final one is just asking basically about integers. So there's currently not any negatives in the tree. So the question is, the tree can only accept positive numbers. Well, that's not true, right? Especially since the first one asked us where we would put negative numbers. Right? All negative numbers are going to go at A, right? Which means we can accept negative numbers, right? Because integers can be negative. So those are your final answers. You should have answered true to any negative number being at A, 3 being at B, 6 being at D, no numbers being able to be placed at F, one number being placed at B, and that's it. Everything else was false. So question 3, again, this question had a typo in the original version of the exam. It was corrected, but I think some of you used the incorrect version. So I tried to give at least partial credit to anybody who answered it that way. So we're given the following binary search tree in the format that we used in class, as well as the format that you have in your labs, so it's supposed to be that the left child always comes first, and the children of a node are vertically in the same place and connected using these lines. So 0 has 2 children, 3 and negative 3. Negative 3 is its left child. So the question is, what would the tree look like if we wanted to remove 0? So we want to remove 0. So that means we need to use the complicated part of our binary search tree removal method, right? And then it asks us to fill in the blank here as to where each of the nodes would be. So I made a note here that actually the way I did it in class and the way it is in your book is slightly different. Both were acceptable. So I'll go through both in this video as well, just so you have proof of that. So we should start by turning this into the sort of tree that we normally look at, right? Again, negative 3 is the left child of 0. Its left child is negative 5. Its right child is negative 1. Because remember, negative 5 is smaller than negative 3, and negative 1 is bigger. And it's opposite over here. So we want to remove 0. And the way we did it in class was I said, you first go to the right subtree and you find the minimum value. Well, the minimum value in this subtree is 1. So then the rule says, well, once you've selected the thing you want to replace it with, you delete that node and you replace the node you're trying to delete with the one you just removed. So that puts 1 at the root, and then 3's left child is null. So putting it back into the fill in the blank over here, the node labeled A would be 1. B would be negative 3 still. C would be negative 5. Negative 1. E is still 3. F is null, right? Because the left child of 3 is null. And the right child is still 5. In the book, they say go to the left child and choose the maximum value. It's the same idea, right? You're still trying to find the middle point. In this case, it would be negative 1. right? So you remove -1, you replace the root, and you end up with this tree with a little bit of an error there, which means A is, that should be -1. A is -1, B is -3, C is -5, D is null, E is 3 still, F remains at 1, and G remains at 5. Right? So this was the right answer if you follow the book's method. Both of them are correct. They're both valid. They both leave a valid binary tree. And that's really what we're looking for. Right? We got rid of 0, and we left a valid binary tree. So question 4 wanted you to use this code snippet that we have here. And it asks 2 questions relating to it. One is, what's the running time using big O notation in terms of n, right? In terms of n. And the other is the value after running it with specific values of n. So how do we analyze the running time? Well, we start to count, how many operations are done. So we start looking at operations. This first line, it's an assignment and a multiplication. So really, it's not one operation. It's 2 operations, right? A multiplication and an assignment. And then let's ignore the loop for a second and start going in to the actual commands here. Well, the if statement is 1 command, and then the subtraction is 1 command. The else is sort of 1 command. The return is 1 command. So inside this loop, right, this whole thing here is four operations. And then we analyze how many times we run the loop. Well, we run the loop 2 times n times, right? Because I goes from 0 to 2n. Notice that that's not n squared. That's 2 times n. Which means, all in all, this code runs 8 times n operations, which makes the answer to the first question O of n, right? Because remember, big O removes the constant, which is, in this case, is 8. And then the second part of the question asked us to trace this code snippet, both when n is 1 and when n is 4. So let's start with n of 1. And so then when we run this guy, we define this variable rtn as 1 times 1, which is 1. And then we start running the loop, right? We start with I of 0. I is obviously less than 2. So then we go in and we check the if statement. Well, I is not greater than or equal to 1. So we run the else, which means we add 0 to rtn. And then we come back up here. Now I is 1. 1 is still less than 2. And then we get here, I is greater than or equal to 1. That's true, so we run the subtraction. And we subtract 1 from rtn, which leaves rtn of 0. And that brings us back here. But now I is 2, and 2 is not less than 2 times 1. So then we leave. So then when n is equal to 1, rtn is going to be equal to 0. And then we run it with 4. So after we run this first command, rtn is 16, right? 4 times 4. And then we start the loop with I equals 0. 0 is not greater than 4, so we add 0. And then we come up here with I of 1. 1 is still less than 8, but it's not greater than 4. So then we add 1. I is 2. 2 is still less than 8, but it's also less than 4. So we add 2. So RTN is 19. We keep going with 3. So then RTN is 22. And we get back up here. And I is equal to 4. 4 is still less than 8. So we still run this loop again. But now 4 is greater than or equal to 4. So we run this inside. We run the subtraction. And we subtract 4 from 22 to get 18. We come back up here. I is 5. 5 is less than 8, but greater than or equal to 4. So we subtract 5 from RTN. 6. 7 is greater than 4. So we subtract. And then we get back up here, and I is equal to 8. 8 is not less than 8. It's equal to 8. So then we're done, and we're left with RTN being equal to 0. So when n is 4, RTN is equal to 4. In fact, no matter what n is, RTN will always be equal to 0 at the end of this loop. So finally, question 5. We're assuming we have this linked list class, and we want to fill in the code for this recursive method that we have down here, this recursive method. I gave you the constructors just so you can see it, but you don't really need to know that. You really only need to know that your pointer is called next, and your data is called value, right? And what we wanted our method to do is determine whether or not the list that we're looking at contains any non-positive values. So anything that's negative or 0. And we were told that we needed to do it recursively. So that sets us up to do this, right? So when we write a recursive function, we really need these two things, right? We need our base cases, base cases, and then our recursive call. So what are our base cases in this case? Well, we sort of already know one, right? If our value is negative or 0, we got to return false, right? So we're going to check our value. If it's less than or equal to 0, what are we going to do? We're going to return false, right? We've already hit something that violates that condition. Otherwise, we're going to keep going. So that means that we are a positive value. And if we reach the end of the line, then we know there's no negatives after us because we're the end. So to check if we're the end of a linked list, we check to see if our next pointer is null. If our next pointer is null and I wasn't negative, then yeah, the whole list, as far as I know, from me on, contains only positives. Otherwise, we know we're positive, we have a positive value, and we have a next pointer. So whether or not our list contains negatives really depends on our neighbor. So then we need to make a recursive call, and that recursive call just returns our neighbor's value, right? It's basically like everything up to, so I'm positive, right? I have a positive value. So I can only, my list can only have a negative if my neighbor, his list has a negative. So just return whatever he returns. And that's it, right? It's really just 3 lines. You have your 2 base cases. One is if you're negative. One is if you're the last guy in line. Otherwise, you're really just asking your neighbor whether he has any negatives in his list. All right?